supervised learning we have seen last time. Now, last time we discussed about regression problems. Today we'll talk about classification problems. What is the meaning of classification problems, use cases of them. Then we'll talk about logistic regression, decision tree, random forest, gradient boosting. We'll discuss about the accuracy parameters and what are the common issues we face in a classification model, overfitting, or as a matter of fact, that can be extended to regression problems or any other data set like null value treatment or outlier treatment, data which is imbalanced, right? And that will be done using Python. So today's session, it will be slightly code heavy. I have 3 Python notebooks over here, right? And all these notebooks I'll again upload to the GitHub link. Yeah. Okay, so let's start with today's work. Okay, so first of all, we understand about supervised learning problems. Supervised learning problems are where you want to predict a variable, a target variable, right, based on the independent variable. So let's say you want to predict that what is my sale going to be, what is my revenue going to be. That is a supervised learning problem. But that supervised learning problem, it falls under the purview of regression problems. Classification problems are those where you want to predict a categorical variable. That means, will the customer shop with me or not? Will the customer churn in the next 90 days? Is this credit card transaction a fraud transaction or a genuine transaction? Will the customer fly with me in the next 30 days, or will the customer buy this particular route, right? If I'm launching a new product in the market, will that be successful? Or let's say if I move to the manufacturing phase, if I use a combination of mold 1, mold 2, mold 3, this temperature, this pressure, will my manufacturing yield, will it go above 95%, right? Or let's say in drug discovery, okay, in clinical trials, based on the patient's historical trends, will that be a successful medicine? So the use cases of classification problems are many, right? They are for retail, banking, or BFSI rather, right? Banking, financial services, aviation, telecom, healthcare, manufacturing. You name any domain, you would find examples of and use cases of classification learning problems. Okay, and that is why they are very popular in the data science world. So just a small tip for the people who are going to attend interviews. It is very highly likely, very highly probable that you will be asked a classification learning problem during your interviews. By giving your case study, or by discussing about the algorithms. The important questions will be that how will you measure the accuracy of the solution? How will you choose the best algorithm? And how will you deal with the common problems in the data set? We are going to deal with all these questions today, but just a heads up to you. Yeah. Okay. So there are plethora of classification learning problems, algorithms. I won't go into each one of them, but if I want to give you a list, there will be logistic regression, decision tree, random forest, gradient boosting, naive Bayes, k-nearest neighbor, support vector machine, then the likes of neural network. Bayesian stats also plays a very important role. So there are ample of algorithms available for that. Today we are going to discuss 2 or 3 of them. But that being said, it is good if you understand the logic behind them, at least the basic concepts behind them, right? Okay, so we'll start with the logistic regression algorithm. It is one of the simpler algorithms, and it is generally the very first algorithm which we test, and you can see on the screen the equation of a logistic regression model. So the difference between linear regression and a logistic model is this one. That this is the equation of a linear model, y is equal to mx plus c, and this is the equation of a logistic model. That way the probability score is 1 over 1 plus e to the power minus b2 plus b1x. So basically a linear model has been converted to a logistic model. Okay, or not, it will be incorrect for me to say that converted to logistic model. It is more like, it's an equation, or it's a solution which you can use for working on your classification problems. Now your classification problems can be either binary or can be multi-class. That means good, bad, yes, no. They are binary classification problems. Okay. Your multi-class classification problems will be that if you want to, let's say predict that what is my my customer prediction for a particular uh, particular uh, particular uh, review that the customer has given, good, bad, ugly. Now that is a multi-class classification problem. Okay. So that is the meaning of your classification problems. Okay, and over here we can use the logistic regression. If we talk about the decision trees are the most, again, very simple algorithm that can be used. So we have the root node over here, we have the decision node, splitting that we have seen in the last time, that we have our splitting done, and finally the splitting is based on a few parameters, right? The parameters are last time we discussed about the variance, which is for the regression problems. Today we are going to discuss about these three: Gini index, entropy, and information gain. So these three can be used for your classification trees, right? Gini index, it refers to that, the objective is to make the nodes, these output nodes, very pure. Okay, so for them, these three are the three criteria. I won't go into much detail. I will again share these slides to the GitHub, but the objective is that I want to create my nodes which are very pure. That means they should have one class in the ideal case scenario, not more than that, right? Practically it won't be possible, but we'll strive to achieve one class in the terminal nodes. Now, if I take a step back from there, logistic regression, it is generally the very first algorithm which we test or which we try to build upon. It is followed by a decision tree algorithm. Okay, generally as a benchmark, we do test our solutions on these two algorithms. Decision trees, they are prone to overfitting. We will discuss about that, how can we tackle overfitting in a while. But decision trees, they do have a problem that they are prone to overfitting. Logistic regression, on the other hand, they do not suffer from such a big issue, but they can still overfit. Okay. Now, ensemble learning, bagging and boosting algorithms, you have discussed the concept last time about the random forest algorithms and the boosting algorithms. So long story short, what they do is that instead of taking only one algorithm at a time, or instead of believing balance or placing your trust only on a single algorithm, ensemble learning is a collection of small solutions. Like in bagging or in random forest, what happens is that sampling of the data set is done, right? And multiple decision trees are created. That's why random forest, right? Multiple decision trees are created, and towards the end, a voting of that will be done. So for example, if you want to predict that is this credit card transaction a fraud transaction or not, so I will create multiple decision trees for them, and after then, after we have created all those decision trees, a voting will be done of all. Okay, and if the vote is that yes, the transaction is fraud, it will be classified as a fraud transaction, else vice versa, whatever it is, right? On the other hand, boosting, it intends to to work upon the last iteration. It focuses on the misclassifications of the last iteration and then tries to improve the algorithm, right? So that is boosting. You are boosting on your previous iteration. The most famous one is the gradient boosting algorithm, right? Which is one of the very famous algorithms for ensemble learning. Okay, we'll again discuss both. We'll again look at the codes of both of them. And we have discussed the concept of bragging and boosting last time. Now comes the important part. How will you measure the accuracy of a solution? So let me open, yeah, this one. Now this thing over here, which I'm sharing on the screen, the confusion matrix. Look here, please. Now this is the confusion matrix. Okay, confusion matrix is the most widely quoted and widely used accuracy measurement process for classification algorithms. Not only in the machine learning, the classical machine learning algorithms of regression and decision trees and all of that. Even for the neural networks, we use them. So, like you can see over here, what we do is we have actual condition, we have predicted condition. The one that are on the green, they show that you said the actual tag was the transaction is fraud. The algorithm predicted transaction is fraud. Okay, good. That is a correct classification. Similarly, this 121, all these are make-up numbers. This one says that the algorithm says the actual condition says that the transaction is genuine. Algorithm also predicts the same. Good. Algorithm is doing a good job. These two over here, they are the opposite. Algorithm said yes, the actual was yes, algorithm said no. Actual was no, algorithm said yes. Okay. Now this is the confusion matrix for binary classification. It can be extended to multi-classification model also. Okay. Now, based on this confusion matrix, we can create very quite a few other matrices, like for accuracy. Accuracy means that out of all these instances or all these observations, how many observations were correctly classified, which is 465 plus 121. They were correctly classified by the algorithm. And that is my numerator. Denominator is my total observations. Okay. Then we have precision and recall as two important KPIs. Precision means that out of all the predictions which you made as positive, how many are actually positive? So you said that the out of 1000 you predicted that 1000 transactions are fraud. Out of those 1000 transactions predicted by the model as fraud, how many are actually fraud? That is precision. Okay, so the algorithm said that X are fraud, how many are actually fraud? That is precision. Recall on the other hand says that out of 1000 transactions which are actually fraud, how many you are able to detect? What it means is that the real world scenario or the real world tag was that X transactions were fraud. How many you were able to detect? That is the recall. And then there are other KPIs like false negative rate, false positive rate, multiple other KPIs are there. All these KPIs, they are very important for different business problems. Like for example, if you are, let's say, if I take the same example of credit card fraud transaction, you would want your recall to be high. Why? Because you do not want to let go any fraud transaction, right? You do not want to let go any fraud transaction. So in that case, your accuracy will not matter to you. Your recall will matter to you, right? And that is why your business problem, it defines the KPI which you want to optimize. Okay. So confusion matrix is the universal source of truth that is assessed when we build a classification learning problem. From there, we get the next set of measurement criteria that is called the ROC curve. So the ROC curve, this represents the ROC curve over here. You have your false positive rate, you have your true positive rate on the x-axis and y-axis, and this line, it represents 0.5. Why 0.5? Coin toss, right? So your algorithm has to be at least 50% accurate. These respective lines over here, they are different versions of your algorithm. So you iterated with 1, 2, 3, 4, 5, 6 algorithms. So from this is called ROC curve, a receiver operating characteristics curve. And from each of these algorithms, we get AUC value, area under curve value, right? This is the area under curve, right? Whichever algorithm gives us the best area under curve, that is the best algorithm for us. Okay. Then there are other, so again ROC curve, but ROC curve, they are a byproduct of your conversion matrices to a certain extent, because you are just testing that what is my false positive rate and true positive rate. So intrinsically, you want to have your conversion matrix at least, right? Then there are other parameters which are AIC, BIC values, KS stats, Matthew correlation coefficient, multiple other parameters are there. I am not discussing each one of them due to shortage of time, but again, like I mentioned, the slides are uploaded to GitHub. Please feel free to explore them. Okay, I would talk about the challenges that we face in the machine learning algorithm. So first of all is the overfitting or underfitting, that is referred to as a bias variance trade-off. Now, what happens is, if your algorithm is too simple, it's very simple, right? In that case, it is an underfitting model. Okay, what will happen is that your model is not able to work on the training data itself. So how will you identify that? If your training accuracy, let's take a step back. So what you do, you take a data set, you divide into train and test. If your training accuracy is low, that means the model is underfitting, right? If your training accuracy is high, testing accuracy is low, that means model is overfitting. Now, how to deal with that? If the model is underfitting, that means you have to increase the complexity of the model, and you would have to look at the dataset also. It is a possibility that dataset does not have any relationship. Okay, if the model is overfitting, then based on the algorithm, you can take multiple actions. Like for example, if it is a decision tree, you can prune your decision tree, right? You can decrease the overall, you have to decrease the complexity of the model. So just to, if I show you what is the meaning of overfitting. So if this is a model, let's say if I talk about an equation in that form of an equation. So your model is very complex, so complex that it is able to model for each and every of the training data sets. But the moment it will hit the testing data set, it falls below. That means it won't work on the real world problems. So you have to decrease the complexity of the model. And what it means is that you have to tune your hyperparameters. Like in the case of decision tree, you can tune about your number of leaves, the tree depth. In support vector machine, you can talk about your cost functions, right? Okay, so these are the methods you have to treat. You can go for your overfitting. Okay. Then there are other problems which are imbalanced data set, null values, outliers, and categorical variables. So these three we will explore in the code. Okay, categorical variables, I'll just discuss categorical variables right now. So what is the meaning of that? So sometimes you would get categorical variables, like for example, gender, okay, or let's say city. Now, if the let's say the data set is like this, customer ID 1, 2, 3, 4, gender is male, female, male, female, okay. What one hot encoding does is it does like this, right? 1, 2, 3, 4, 1, 0, 0, 1, 1, 0, 0, 1. So you can see that it has converted this categorical variable to numeric variables. But obviously, if the number of classes are high, let's say if we have city, let's say New York, New Delhi, London, right? Let's say Limerick, okay, and Tokyo. So in that case, it would create 5 variables like this. New York, New Delhi, London, Limerick, Tokyo. And for each of them, it will be like something. One, the rest of them will be 0. So the problem can be that your data set will become very sparse. There will be so many zeros inside it, first thing, and the number of variables they also increase. That is why we have to use it with caution. Okay. Now I'll discuss about these 3 things: imbalanced data set, null values, and outliers. Okay. So yeah. Okay. So first of all, imbalanced data set. What is the meaning of imbalanced data set? If your data set has, so let's say you have 1,000 or 10,000 observations, right? And out of those 10,000 observations, you have one class as yes, one second class as no. Your target variable is yes and no. Your target variable, your yes is 5, and the rest of them are no. That means your data set is imbalanced. Why does it matter? It matters because if your algorithm classifies all the observations as no, it will be 99.95% accurate. If it classifies all the observations as no, right? But it won't be a correct solution. That is not an ideal solution. It is not doing its job to identify the yes. So let's extend this example to real world. If you have credit card transactions, and in 1 billion transactions, you might get 100 transactions as fraud. So if your algorithm predicts all of them as genuine, as non-fraud, you would get 99.99999% accuracy, right? But that is not the correct solution which you want to have. That is why we should treat our data imbalance. Now, what are the ways to do that? So the first way is that you oversample this class. The underrepresented class, you oversample that. The one I'm doing, I'm marking in yellow. You oversample this. Okay. Other way can be you undersample this. The overrepresented class, you undersample this. So take more samples from this. So let's say if I, instead of, if I'm taking a sample from this, so let's say I'll take 100 examples and all 5 and 95 from here. So in that case, the class imbalance has decreased a lot. That is oversampling from there. Now, if I take, let's say, a different set over here, let's say if I take 100 examples and 1 from here and only 10 from here, right? Now, the problem with oversampling or undersampling is that they change the structure of the data. So the overall structure of the data was not this, it was different. And that is why oversampling, undersampling, they do not lead to a very robust solution. And that is why you have solutions like SMOTE. Okay, so what is SMOTE? Look here. So first of all, I'll discuss about SMOTE in a while. Let me show the code for that. So let's first create. So these are the libraries which you have imported. Classification. This is a scatter plot, let's say, of the underrepresented class. So 1 is the underrepresented class, over 0 is the overrepresented class, and this is SMOTE. Okay, so what SMOTE does is it creates, or it synthesizes, you can say that, more examples of the underrepresented class, right? And then they are selected in the while we are doing the sampling. Okay, SMOTE, it is like a data transform object. It is the full form. It is synthetic minority oversampling technique. Okay, so what it does is, this is a simple implementation of SMOTE, that I invoked SMOTE and I'm using it to resample my data set. Okay, like, if I have, again, over here I'm defining my sampling strategy for SMOTE, that I want to have 0.1 or 10% as my sampling strategy. Again, over here I'm using the pipeline and the fit resample. This code I'm uploading to GitHub, and you can use it from there, right? This is SMOTE, and you can use it for dealing with your imbalanced data set. Okay, it will allow you to maybe to a certain extent, deal with imbalanced data. Like, for example, in this example, earlier we had 9900 or 9900 and 100 as the two classes. By the end, we had, like, when we treated them equally, they are equally created. If I want to create a 10% of that, that is 1980 and 990. So based on the requirement, or based on my understanding, I can oversample my minority class over here, okay, using SMOTE. Fair enough. Now that was SMOTE. The second question is null values. What is the meaning of null values? In your dataset, you would get a lot of missing values, null values, blanks, and they are a nuisance to the analysis. Now over here, one simple way is that to simply drop those observations, but that is not a correct solution, because you are losing dataset, you are losing critical information. Okay, second solution can be that you impute those missing values with the mean. Like, for example, let's say if you have cust ID, you have revenue, right? 1 2 3 4 5 6 7 8 9 10. So you have, let's say, again 100. Let's say, let me do it like this, right? And let's say this is missing and this is missing. Okay, so if I have to impute these missing values, I can take an average of them and impute the missing values with them, or I can impute them with median. That is also one of the solution. In case of categorical variables which are missing, which are missing values, I can have mode. But in that case also there is an issue. The issue is that mean or median, they are treating all of the variables or all of the observations alike. They are not a scientific method to impute the missing values. So for that we have again a missing value treatment, that you can use k nearest neighbor as an algorithm to impute your missing values. So what happens in k nearest neighbor is, again, k nearest neighbor can be used for classification problems also. So the theory behind k nearest neighbor is, k nearest neighbor. So what it means is that, let's say, you have this as observations, these as observations. I'll zoom in. Yeah, observations, right? And these as observations. Okay. And now you have a new incoming observation. Now let's say new incoming observation lies over here. So the concept of k nearest neighbor is that we will check the neighbors around this new incoming observation, and whatever the neighbors are, we will assign that value. So if this new incoming observation lies over here, in this case they all are its neighbors. Okay, that is the objective, that is the concept behind k nearest neighbor. So using k nearest neighbor, we can impute our missing values. So there is a KNN imputer, right? And using KNN imputer, we can impute our missing values. Okay. Again, I'm not going into the complete depth of that. Now you can take the code from the GitHub profile, GitHub link, and work on that. Okay. One important thing to note is that k nearest neighbor, k is a very important KPI. Based on different values of k, your solution's performance will change. And hence, in this example, we have tested with different values of k. What is the value of k? How many neighbors would you take? So let's say if your incoming observation is like this, so will you take 2 neighbors? Will you take 4 neighbors, right? Because based on all of them, your solution or your answer will change. That is the impact of k. Okay. The next one is the presence of outliers. Outliers, what they mean is that, let's give you an example. If you have if you're working in a manufacturing plant, and generally your pressure in the manufacturing plant of the machinery, it is like it ranges from 1 to 5 bars, but one fine day it increased to 200 bars. That is outlier. Or let's say you have a customer, right, or 100 customers, and those 100 customers, they make phone calls of 100 minutes in a month on an average. In a month, in a particular month, it dropped to 0, or in a particular month it increased to 1000, right? So they are the examples of outlier. Like, for example, on a New Year day, a person is sending 5000 SMS, as compared to in a normal day a person does not send any SMS, right? So that particular day will be an outlier. How does the outlier impact the solution? Outlier, they make the equation fit itself to include outlier. Like, what I mean by that is, if your model is like this, if your data set are like in this zone, okay, in this zone only, but you have one observation over here, your most observations, let's say, are over here. So your plain simple equation could have been this one, but with outlier it will tilt, because the algorithm will try to accommodate this outlier observation too. Okay, so in that case we treat outliers too. The simple way to treat outlier is that you cap them. That means whatever is beyond 95th percentile, it will have maximum value as 95th percentile or 98th percentile. Similarly, on the lower values, lower cap side, you can say that whatever is less than 5 percentile, I would keep it at 5th percentile only, or whatever is below second percentile, I would keep it at second percentile only. Okay, what it means is that, if your observations are, let's say 1, 2, 3, 4, and let's say your 75th percentile is 3. So if the value is coming to be -10, I would replace -10 with 3. Or the value is coming as, let's say 100, I would replace that with 4. Okay, but a word of caution: outlier treatment and null value treatment should be done with caution. We should first of all look that, are they by design, or are they not is there any data collection problem? Like, for example, the pressure example which I gave to you earlier, it is a possibility that whenever the pressure increases, then your machine fails. So in that case, it is not an outlier. It is an important observation for you. Yeah. Okay. Now let's discuss about logistic regression. So, we have a case study over here, and I won't go into that. I will just talk about how do you do that. So you have your model over here, you have your train test split, your credit risk model is over here, you have your target variable is that whether the loan will be approved or not. Okay, and over here you can see that the challenge is not the model in itself. The challenge is data preparation for that. That's what we are trying to do. We are trying to assign the null values. We are trying to assign some relationships. Okay, and these are all under the purview of EDA, exploratory data analysis. And over here you're doing your train test split. Okay, this is your logistic regression model. This is the output of your logistic regression model. Okay, and the way to identify that which variables are significant or not, you can simply look at their p-values. We discussed the concept of p-value last time. If the p-value is less than 0.05, we can say that those variables are significant for the model. Okay, now this is one thing. They are the respective coefficients for them. Okay, if you want to build scikit-learn, if you want to use logistic regression of the scikit-learn library, that also can be done. We can do, like, over here you can see that we have the scikit-learn library, and from there we have a logistic regression model. What it means, random set, what it means is that if you want to reproduce the results, you can have a random set equal to 42 or 10 or 5 or 6, whatever. Ultimately it's a number which is used to reproduce your results. Okay, and this is how this is the confusion matrix which we were discussing earlier. You can use this code to draw your confusion matrices. This is your ROC curve. Okay, similarly you can have your decision tree. We have seen this code last time, or a part of that, EDA and all of that, right? This is the correlation matrix. Correlation matrix will tell you what is the correlation between all your independent variables. Okay, this is the tree based method again. Where here, just hold on. This is your decision tree classifier, right? And you can see that you just have to create your training and testing data. Like earlier, this is the train test split we have taken, right? Train test split in the using the scikit-learn library, right? And using the decision tree classifier. One second. Yeah, using the decision tree classifier, we have built the model for that. Now over here, this is the visualization of that, right? If you want to prune your tree, or to because you can see over here that the model is kind of overfitting. So if you want to reduce the overfitting of the model, you can do that. I will load the code for that also. This is the random forest classifier. Again, random forest classifier, fitting, training, and testing data, predicting on the testing data. Sorry, fitting on the training data, predicting on the testing data, and then we are getting the accuracy. Like in this table, we are simply adding the accuracy of decision tree, random forest. You can see that random forest has a better accuracy. Then we have AdaBoost classifier. So one point to be noted is that if you can see that scikit-learn library, it has everything. It has all of your classical machine learning algorithms of decision tree, logistic regression, which you have seen over here, right? Logistic regression, you can see over here, it can be used to create. So scikit-learn can be used to create your logistic regression, your decision tree, your random forest, your AdaBoost. You will see that it can be used for gradient boosting algorithms, right? So basically, you can use scikit-learn for each of the algorithms, okay? And the process is simple. You divide into train test, you fit on the training data, you predict on the testing data, you build your confusion matrices, and you assess that how good or how bad your algorithm is. Okay, this is my gradient boosting classifier, and again I'm testing. So these are the respective accuracies of a model. Now one question comes to our mind is that how will I choose the best model? So the way to do that is quite simple. Let's say you have your logistic regression as one iteration, LR2, decision tree 1, decision tree 2, random forest, let's say gradient boosting, right? So you create your model, and sorry, you take different KPIs, let's say accuracy, recall, precision, right? Your AIC, your BIC, your K-stats, multiple parameters you can take, and it will be for training, testing, right? Generally, you have a validation data set also, unseen data set which you have never ever shown to your model, and it is advisable you take an out of time data set also. That means, let's say if you have used 2016 to 2018 data set to build your model, use 2019 data set as out of time data set which you have never ever shown to your model to test the accuracy of a model on 2019 data set. Okay, and that will tell you what is the real performance of your model. So between all of these data sets, your algorithm should behave very well on out of time and validation data sets, because if it is behaving very well on training data set, it does not matter, because it has been trained on that data set, it is bound to behave good on that training data set. So even if it is behaving good on training data set, we should not be very happy. If it is behaving very well on validation and out of time data set, then the model is a robust model. You know why? Because ultimately my objective is to predict on unseen data set, on incoming new observations which have never been shown to the algorithm. If the algorithm is able to generalize well, if the algorithm is intelligent enough to work on any observations, it will work very well on unseen data sets. And that is my observation, that is my objective, right? That I will use historical data to train my algorithm, to make it capable enough so that it can work on unseen new observations. So that is how you would choose your best algorithm. A point to be noted is that it will depend on the KPI which you want to optimize. So if recall is the KPI you want to optimize, you would choose the best model which is giving you very good recall percentage. Just a small thought over here, that if you have, let's say, model 1, model 2, model 3, right? If this model is giving you train and let's say test, let's say 98% training accuracy, 70% testing accuracy, overfitting. Okay, 60%, 58%. Not a very fantastic model. But let's say if it's giving you 81% over here and 79% over here, it's a good model. Right? Though the training accuracy is lower, but it is a very good model as compared to this guy. And let's say in the validation 2, let's say if it is giving me 65%, it's giving 55%, 77%. A good model. No? Because if you see that model 3, it's consistent. It is giving me easily 75% accuracy always. Right?